So hello again, this is structural analysis, and in this video and some structural design made fun and easy. This is going to be analysis and design of a simply supported steel beam to BS5950, as shown in the diagram. As a little look at the beam setup. So this is a typical postgrad level 7 MSc style question. Yeah, please like the video and subscribe to the channel so you can get more videos as I'm going to carry on, hopefully. So basically, this is the analysis and design of a simply supported steel beam. Just a note that I wanted to add in first is that for steelwork beams, I'm a structural engineer with 28 years experience, and I have actually never designed a continuous steel beam, and it sort of occurred to me that I should just make a note of this in this video. All the steel beams that I've done always been simply supported, and I actually believe this is because of the difficulty of making steel beam continuous over the supports. It's not like reinforced concrete, so you can't put bars through the columns and things like that. So just really that to do steelwork design, you really need to understand simply supported conditions. Very helpful to think about that when you're going into it. Not that you won't be doing continuous steelwork using support moments. So in this example, we've got to design a simply supported beam. So I'll just run through the question dynamic setup. So the question says that we've got a 406 times 178 times 74 UB section in grade S355 steel, which is simply supported, spanning 8 meters. It is required to carry an unfactored, uniformly distributed dead load of 20, including the self-weight. So that's important because it's including the self-weight. Won't need to add on another 74 kilograms per meter in the calculations. So that's already been taken into account according to the question. It's clearly saying it's including the self-weight over the entire span. And then we've got with 100 kilonewton unfactored live loads at each end 2 meters from the support. So here's a diagram of the loading condition and the beam. We've got support A here, support B here, simply supported. And we've got dead load, UDL, 20 kilonewtons per meter squared, 20 kilonewtons per meter, and we've got, that's a dead load, that's unfactored, and we've got 2 point loads, 100 and 100, 2 meters from the supports, and that's a live load. So so there's a little bit of exam technique to just think about during this question. So this question is worth actually 20 marks. I worked out that we've got 36 minutes in the exam to do this question. So that actually gives you, I worked out as 1.8 minutes per mark. So the first part of the question is determine the maximum bending moment on the steel beam due to the factored loading at the ultimate limit state. So, and it says within the questions that the tables they provide with the section properties of the steel beam may be used in this question. So firstly, this video is going to be part 1 of 2, as it's already, as you can see, it's quite long, and we're more than 5 minutes long, so I thought I'd just break it in half. So we got to, so the first thing to do, we as you've seen in my other videos, we've got a simple supported beam, we've got to use simple methods, simple statics to determine the forces, reactions and deflections, the forces, moments and deflections in the beam, and then we can design the section or check this section works once we've got the forces. So, and there's a new technique that I'm just gonna introduce for this one, but I'm going to do a separate video on this, and that's we can use the principle of superposition. That's just where you can work out moments and forces from one force and then just add them together to get the total bending moment. So we can work out the forces from the UDL, and then we can work out the forces from the point loads, and then we can just add them together and we get the total forces and reactions. So first of all, so that's how we're gonna tackle the problem. Then we're gonna start with the load factors. So the question is designed to BS5950. So as you probably already know, dead load factors are the factor of safety for the dead loads is 1.4. The factor of safety for the live loads is 1.6. So you can see in here the dead load is 20, so we need to times that by 1.4. It's including the self weight, so we don't need to worry about that, as I said. And then we've got 100 and 100. We need to times that by 1.6 as their live loads, and then we can work out the forces from here. So the ultimate loads, first of all, so we times 20 by 1.4. That gives us 28 kilonewtons per meter. Just done the work in there by hand. It's 20 times 1 times 0.4 times 20, and that's 4 times 20 over 10, so that's 0.8. So that's 8. So the total is 28 kilonewtons per meter for the UDL, and for the dead loads it's simply 100 times 1.6 gives 160. So if we start off, we got to look at the UDL, the ultimate. We can work out the ultimate moment, because the question says determine the question says determine the maximum bending moment on the steel beam due to the factored loads. So we need the moment. I mean, by inspection we can say that it's going to be somewhere along the span, so we know that for sure. So the first thing to do is to work out the maximum moment due to the UDL. So the bending moment, everyone probably knows this, but it's WL squared divided by 8. That's the bending moment for the UDL. So we just do W, which is 28, factored, dead load, times the span, 8 squared, divided by L. So one of those 8s cancels out, so we just got 28 times 8. That gives us the maximum bending moment due to the ultimate UDL. So that's equal to 8 times 20 is 160, 8 times 8 is 64, adding together you've got 224 kilonewton meters, and that's obviously at span at L over 2, and the length is 8, so the maximum moment is at 4 meters, which is dead center of the beam, and it's 224 kilonewton meters. So that was pretty easy, very easy, simple stuff, just working out the bending moment under the UDL. So that's half, and I reckon that gives us a couple of marks. Actually, I think for this, we have 5 marks for this question. So we actually have 9 minutes to do it. So that's probably worth maybe 1 mark just to find out the correct UDL moment. So then we've got the moment due to the point loads. I'm going to do a separate video on 2 point loads like this on a beam, but basically we can work out by inspection that if we've got a load here P and a load here P, and they're both the same, and they're positioned at the same distance from the supports, and fairly obvious that the reaction is going to equal P on this side and P on this side, but I'll do a separate video on this, on how you basically, we do, done some other videos on this, we do vertical equilibrium and then we take moments about A, if we want to double check that. But you know, if you use common sense, we can say by inspection, P is going to, the support reaction at A is going to equal P, and the support reaction at B is going to equal that P, P2, P1. They're both the same, so 160. So then, if we look at the maximum moment, going to be between 2 and 4 meters, and that's P times the lever arm A, and that's 2 meters. So it's basically going to be 2 times 160, so that gives us 320. So on this position, between 2 and 4, and it's the same on the other end obviously, because if we do, the lever arm again is 2, the support reaction is going to be 160, so the lever arm times the support reaction is 2 times 160, gives us 320. So we know that the moment along the section between 2 and 4, sorry, 2 and 6 it is, between 2 and 6 is equal to 320. Yeah, so if I'll add this diagram into the video at the end. Basically this section is 4 meters long, so it starts 0, first load is applied at 2, then the next load is applied at 2 plus 4, which is 6, and that gives us that little 2 left at the end. That makes up, and the span makes it up. The span is 8, so it's 2. This length is 4, and this length is 2. So the maximum ultimate load is between 2 and 4, which is 320 kilonewton meters. 160 times 2. So if we just add we look at these bending moments diagrams now, we've got 2, so we've got a maximum moment mid-span here, and we've got a large moment, the largest moment is also at the middle here, so we just add we can see from inspection of the bending moment diagrams, the maximum moment is at L over 2 by superposition, so we have 200, the maximum ultimate load is 224 plus 320, and that gives us 544 kilonewton meters. So that's the answer. The maximum, the maximum ultimate design load is 544 kilonewton meters. So that's I reckon that's worth 5 marks. That's the answer for the first part, 544. So now we move on to part B of the question. It says determine the maximum shear force on the steel beam due to the factored load and the ultimate limit state. So again, we've got to use the ultimate loads as calculated in part A, and again we can just simply use the principle of superposition to determine the shear forces for the point loads on the UDL, and then add them together. Basically, I'm doing this thing about superposition because I just thought it would be easier to show that you can just, to make the analysis easier, instead of trying to analyse a beam with the UDL and point loads at the same time, you can just take them, you can just separate them into 2 components and then add them together back. Then you're just doing a UDL and a beam with point loads on it. So the UDL is just, the shear force diagram is basically you've got a reaction at A, the UDL take a continuous uniform along the beam and then back up at support B, so that the reaction at A is basically the UDL times the length of the UDL divided by 2, because it's obviously symmetrical loaded. Again, if we wanna double check this, we can take moments about A. So basically we've got 28 times 8, that's the value of the equivalent, there's an equivalent point load of W, which is 28 times 8, which is 224, and so you say 224 divided by 2 is equal to 112, so the reaction at A is 112 and the reaction at B is 112. Then if we wanted to check that quickly, we can just say 224 times 4, which is half the span, which is the centre of load of this UDL, is equal to 8 times RB. So basically RB is just W over 2 because it's 4 divided by 8. I think in this particular video I won't go into too much detail about this because I've got the answer. I know it's right. We've only got a limited time because again we got 5 marks for this question. It's 9 minutes, so you just got to get the answers as quickly as possible. I think it's obvious that it's correct by inspection. So I mean I have quickly checked it here in the notes. It's so take vertical equilibrium for this beam. RA plus RB, 28 times 8, 224. So that's RA plus AB. Then take moments about B, say. So 8 RA is equal to 224, which is the equivalent point load or the total UDL over the by the length, little w times L. It's a uniformly distributed load. So that gives you 8 RA equals 224 times 4 equals 896. So RA is equal to 896 divided by 8. You just take that 8 down to this side, and that gives you 112. So it's checked, it's correct. So that gives you, that must be worth, I think, I don't know for sure, but I think that gives you 2.5 marks because you've got 5 marks for this part of the question. And then now we've got to find the shear force for the point load. So basically, again, it's fairly obvious that when we just show you again in this diagram, we've got a point load in here, this reaction must equal to this point load, this reaction must equal to this point load. So RB must be P1 and RA must be equal P1 and RB must equal P2. We can check this using vertical equilibrium. RA plus RB equals 160 times 2. And we take moments about B. So we'd have from this side 2 times 160. That's this point load. A point load here. Times 2 plus 6, because it's 2 plus 4, so it's 6 meters to the next one, and that's times 160 again, and that's going to equal to 8 times RA going that way. We're taking moments about B, so that gives you 2 times 160, 320, plus 6 times 160, 960, equals 1280, and 8 RA equals 1280. So RA is equal to 1280 divided by 8. So it's 1, carry 4 over to 48, so it's 6, so it's 160. And we know the that's the reaction at A, and it's equal. Obviously it goes up 160 along, down where the point load is, 160, 0 shear, and 160 down at point load 2, then along to the support, and then back up to 0. So the maximum shear at the support, is 160 plus 112, because we just added and superimposed the one from the point load and the one from the UDL. So 112 from the UDL, 160 from the point load. It gives 160 plus 112, which is 272. and that gives you another 5 marks. So the next part of the question is determine the shear capacity of this section with referenced UB section. So the section size is 406 times 178 times 74 UB. So back to the exam technique, on it's got 3 marks for this. 3 times 1.8 is 5.4 minutes. So I've just done a little diagram for the to show how I'm going to calculate the shear capacity of the section. May know this, but the shear capacity is basically, for a UB section, is on the web. So it's the thickness of the web that carries all the shear, not the flanges don't do anything for shear. As you see here, I've drawn it out. The shear area AV equals thickness of the web times D, which is depth of the section. Depth of the section. The steel grade is 355, remember. So the shear capacity of this section is equal to the factor of safety, 0.6, times the design strength times AV. So that we go to the table. We've got PY equals 355. From the tables, for 406 times 178 times 74 UB, we got T equals 9.5 millimeters and D equals 412.8 millimeters. So that we can't just take the shear from the section tables. In the tables that are provided with the question don't give the shear capacities. You have to calculate it manually. That's the question. So we got the shear capacity is equal to 0.6 factor of safety, 355, which is the shear, which is the design yield strength of the steel, 9.5, which is the thickness of the web, and 412.8, which is the depth. That gives us 835,300.8 newtons, which is 835 kilonewtons. So I think we got 3 marks for that one, and you had 5 minutes. So you have to kind of speed through these really quickly. And then part D of the question says check whether the beam is subjected to a high or low shear force. So again, we got 3 marks. Time allowed is 3 times 1.8. That's 5.4 minutes. In BS5950, we got low shear if the shear load is less than 0.6 the shear capacity. So 0.6 times 835, which we just worked out, 835 kilonewtons equals to 501.18 kilonewtons. And from question part B, the applied load is 272. So as 272 is less than 501.08, we've got low shear load. So I've noticed when I do any design, usually we have low shear load because basically beams will fail in moment or deflection in the test. So this is a bit of a long video, so there's some parts, I think 3 more parts to this question to get the 20 marks, but I'm just going to cover that in part 2 of this video. So this is to be continued in part 2. Please like this video and subscribe to the channel. Thanks very much. Any questions, please leave a comment, and I'll add the text maybe for this question in the description. Thanks.